Hello everyone. Welcome to the presentation of the paper on outdoor thermal comfort, a model based on thermal adaptation in New Zealand. This paper presents a model that was developed to comprehend and test adaptation aspects in outdoor thermal comfort and to see how they influence the thermal comfort assessment based on people's thermal expectations and thermal preferences. And it was initially developed by Darren Walton, Michael Don, and Vince Stravitsky in 2007 in Wellington, which explores the descriptive scales of thermal perception and thermal impressions, and the affective scales, which are the influence of climate on people's behavioral aspects that are involved in the thermal adaptation. The current study expands the methodology of the model that was developed in 2007 to capture more human thermal responses in a much wider climate range and to improve the interpretation of the influence of the climate parameters on comfort by using a renowned thermal assessment model, the Universal Thermal Climate Index, which is also known as the UTCI. Initially, thermal comfort assessment was done with the combination of temperature and wind or temperature and relative humidity for indoors. And later on, a human heat balance model or the human thermal regulation was combined with temperature, wind, and relative humidity to develop steady state models that are mainly developed in controlled laboratory environments. This was a very systematic way of exposing people into various thermal conditions, which is completely opposite to how it works in the real world, where we really cannot control the environmental conditions. Using these steady state models showed certain discrepancies when they were tested in the real world with people's responses. And these differences were initially discovered in the indoor studies, and later on they were identified in outdoor studies as well. The predicted comfort values from these steady-state models are either overestimated or underestimated comfort levels. It was also noted by many studies that the majority of the people who are asked for their impressions on comfort when they are outdoors, they reported they are comfortable. In some studies, it is closer to 90% of the total subject sample. As noted in many studies, adaptation in thermal comfort research is a complex issue, and people do adapt or adjust to the exterior environment in many ways. Behavioral adjustment is one of the main adaptation methods where we change our clothing, the exposure levels to suit and become comfortable in outdoors. Our thermal expectations and knowledge plays a vital part in psychological adaptation where we know what to expect in each thermal environment, especially with seasonal changes. So how are these adaptation aspects are integrated into thermal comfort research? The most popular method is the thermal sensation votes. It is basically the responses of people, how warm or how cold they feel in the current thermal environment. These TSV votes are either regressed with climatic parameters such as sun, wind, temperature, and relative humidity, or, as mentioned earlier, they are used to calibrate steady state models. But does thermal sensation votes provide an insight of the real thermal effect when the majority of people report as comfortable? The multidimensional adaptation model that was developed in 2007 does not actually rely only on thermal sensations. It integrates a number of questions on thermal perception, thermal effect, and behavior that are collected in field surveys through questionnaire interviews and climate monitoring. 18 questions were evaluated in this research and 1,100 responses were collected in 2007 and 2016 and 2017 field surveys. The questions are then analyzed with principal component analysis using SPSS to reveal what questions or variables act together and how they influence thermal comfort in outdoor spaces. These variable clusters are known as components, and in this study, you can see from the graph there are four components or variable clusters that were prominent. The first cluster loaded variables that are related to temperature or warm or cold related questions, and the second cluster is about the time of exposure in the outdoors, and the third cluster is related to the wind environment and perceptions or thermal effects of the wind. And the fourth cluster is related to the thermal preference or of sun and warmth. The first and the third clusters are directly linked with thermal environments and the effects of the physical parameters. And these two clusters are combined together to develop the combined adaptive factor, which is the most prominent or the most important scale in this research. The combined adaptive factor represents the human thermal perception and responses to varied thermal effects that was collected for all 1100 responses, and it shows all the thermal effect in a single scale. This is the alternative for thermal sensation votes, but it is an advanced version where it integrates a number of thermal adaptation aspects, not only the thermal sensations. Tracing back the combined adaptive factor scores to what people responded in the questionnaires, it can be concluded that lower combined adaptive factor scores, or the CAF scores, represent a colder, windy, and a less sunny environment where they prefer to be warmer and to have less wind and more sun. And this is the other way around for the higher CAF scores, where people feel hot, sunny, less wind, and they want to have more wind and less sun. A comfortable range for CAF from 38.8 to 44.7 was identified by mapping the CAF scores with people's responses from the questionnaire for a number of descriptive and affective variables. When the warm or cold impressions are concerned, which is basically the thermal sensation votes, around 80% of the people reported to be comfortable in this study. However, when the CAF comfortable range, which is 38.8 to 44.7, is concerned, it has only a 36% of the total responses, which is a massive difference in the total number of people who will be actually comfortable. CAF is an integrated index for comfort, which is more complex than thermal sensation votes, which gives an insight of the real thermal effect, not the sensation when you are adapted to the thermal environment. To investigate the influence of sun, wind, temperature, and relative humidity, CAF, or the combined adaptive factor scores, are regressed with the physical parameters, which are ambient temperature, wind speed, wind gust, relative humidity, and mean radiant temperature in shaded areas and for exposed areas. Wind gust has a negative effect on outdoor thermal comfort. You can see from the equation, which is in line with actually what people have reported in questionnaires, and it is reasonable to assume that relative humidity does not have a significant impact on overall comfort levels. Thermal Adaptation Index, or TAI, scores are then evaluated with UTCI to further explore what differences the steady state model will provide in terms of the influence of the climate. Thermal Adaptation Index, or TAI, which we saw from the previous equation, and UTCI for all 1100 responses are calculated using the same climatic parameters. And then TAI is adjusted to have the same neutral values as UTCI, and then the two scales are plotted on a 5-degree temperature bracket to see the relationship, which you can see from the graph on the left hand side. And it shows the UTCI and TAI scores follow the same trend, confirming that low TAI scores indicate cold stress and high TAI scores indicate heat stress. However, when it's colder, TAI gives a lower score than UTCI, which means either UTCI overestimates the comfort levels in much colder thermal environments, or TAI exaggerates the discomfort. And it turns the other way around, where UTCI predicts much greater tolerance to warmer climates than TAI. And since TAI, or the Thermal Adaptation Index, is directly derived from the subjective responses through combined adaptive factor, it can be assumed that UTCI have underestimated the heat stress and overestimated the cold stress, which suggests that people in cold climates are relatively adapted to colder environments than what UTCI predicts. The figure on the right shows the distribution of warm and cold responses with UTCI thermal perception scales, and according to this graph, it is much clearer that people are affected by heat and cold stress in warmer and cold climate than what is predicted by UTCI. To provide a summary of this presentation, this framework presents a thermal adaptation assessment method that integrates thermal perception, thermal expectations, behavioral changes, and thermal effect in outdoor environments. Thank you.